Section 3.5 takes a look at how we can graph rational functions. We've already graphed reciprocal functions, which are a special type of rational function. But when we're graphing rational functions, this means instead of graphing functions with something in the bottom, q of x, or whatever that was, like we did with reciprocals and a 1 on top, now we're going to see a p of x, or a function in the numerator, as well. In this case, we're going to find some key info that's going to help us in order to graph the function. So 5 key pieces. First, we're going to want to know the x-intercepts. And the way we find an intercept is we make the other variable equal to 0. So we make y equal to 0. And then when we multiply by the denominator, what this really, in effect, will do is take the numerator and make the numerator equal to 0. And solve that function. And that'll give us the x-intercepts. The second thing we're going to find is the y-intercepts. And just like the x-intercept, we make the other variable equal to 0 and solve that to figure out what the y-intercept will be. The third thing we're going to look for are any undefined points. And undefined points can take one of two forms. If we can factor and divide out a factor, that means there's going to be a hole in the graph. In other words, if a graph would normally have looked like this, somewhere along the way at that point that divided out, there's going to be an actual hole in the graph, a gap in the graph. The other option is if it doesn't divide out, we look at what's left after the reducing, and we make the reduced denominator equal to 0. Because that's going to give us a vertical asymptote. Because the fraction can never have 0 in the denominator, it's going to give us an undefined point, which will either be a hole that divides out, or more often a vertical asymptote that the graph is going to grow closer and closer to. So those are our undefined points. The fourth thing we're going to find is any other asymptotes. And these other asymptotes can take one of 3 forms. One is if the degree of the numerator, actually let's start with the denominator. The degree of the denominator, because that's what we're really interested in, is greater than the degree of the numerator. In this case, if the degree of the denominator is bigger than the degree of the numerator, the denominator is going to be considered bigger, taking over, and we're dividing by a big, huge number, and so basically we'll get a horizontal asymptote at y equals 0. For example, we have x to the 5th over x to the 7th. That's going to reduce down. The denominator is going to take over. We're going to divide by a huge 7th power. It's going to give us 0 for the horizontal asymptote. Now, if the degree of the denominator is equal to the degree of the numerator, we will reduce leading terms. What I mean by that is if we have like 15x to the 7th over 3x to the 7th, and then there's 6, 5, 4, 3, 2, 1. But the leading terms were the x to the 7ths. Here we can reduce the x to the 7ths out, and 15 over 3 reduces down to 5. And so that is our horizontal asymptote. The other option we have is just the opposite. If the degree of the denominator is less than the degree of the numerator. Then we say that the asymptote is a curve. And I use the word curve lightly because it might be a straight line. It's just a diagonal line. And what we'll do in this case is we will use long division, or synthetic if we can, to find the slant asymptote. The last thing we're going to find about all these graphs in order to graph them is the positive and negative regions. And the way we find the positive and negative regions is we take this function p of x over q of x. That is our rational function. And we're going to write it as a product. We will write p of x times the q of x. We will multiply the top and bottom together and graph this part. Because both graphs of the division and the product, both graphs have the same sign. Because if a positive is divided by a positive, it's the same as a positive multiplied by a positive. They're both positive. Positive divided by a negative is the same as a positive multiplied by a negative. They're both negative. They have the same sign. Now what's important to note about these two graphs is that they have no other connection. It's just easier to graph a product than to test quotient. So we'll graph the product just to see where is the graph positive and negative. And that's all we'll care about on that graph. Then we'll discard it. Take that positive, negative information and translate it onto our rational functions. So 5 things to find. You should know how to do all 5 of these before the test, preferably before you come to class today. The x-intercepts, the y-intercepts, the undefined points, the other asymptotes, and the positive, negative regions. We're going to do several examples where we're going to work through all 5 of these steps and see how they translate into graphs. So if f of x equals x minus 2 over x plus 2. First, we're going to find the x-intercepts. To find the x-intercepts, we make the numerator equal to 0. X minus 2 equals 0. And if we add 2 to both sides, we get x equals 2. There is the x-intercept. The y-intercept is we make the x's equal to 0. So we have 0 minus 2 over 0 plus 2 gives us negative 2 over 2, and so the y-intercept is at y equals negative 1. Next, we need to find the undefined points. The undefined points are when the denominator equals 0, and it's either a whole or a vertical asymptotes. This graph's not going to reduce at all. X minus 2 over x plus 2, that's not going to reduce. And so all we need to do is make the denominator equal to 0, subtract 2 from both sides, and x equals negative 2 is going to be a vertical asymptote. So to review what we've done so far, we made the numerator equal to 0 to find the x-intercepts. We plugged 0 in for the x's to find the y-intercept. And we made the denominator equal to 0 to find the undefined points. To find the other asymptotes now, we take the leading coefficient of the numerator, which is x. I should say other asymptotes. The leading coefficient of the numerator, which is 1x, over the leading term of the denominator, which is 1x. Those both have the same degree on them, so that's going to reduce to 1 equals y. This is your horizontal asymptote. The last thing we have to find is the positive and negative regions. And to do that, we graph the product of the numerator, x minus 2, times the denominator, x minus 2 times x plus 2. And when we graph that, x minus 2, x plus 2 have intercepts at 2 and negative 2. The x squared, if we were to multiply those together, x squared would be positive, so it's a positive x squared, so it's going to come in from one side, come out the other side. This graph is going to have the same signs as our graph, so it's going to be positive on the left, positive on the right, and negative on the center. Better said, it's going to be positive from negative infinity up to negative 2. Union, it's going to be positive again from 2 to infinity. It's going to be negative in the middle from negative 2 to 2. So let's see if we can combine all this information together. I'm not going to be able to fit it on the same screen, so we're going to do a lot of scrolling. But we're going to combine all this information together to make our graph. Okay. First, the x-intercept is at 2. So on the x-axis, we'll have a point at 2. The y-intercept is at negative 1. So on y, negative 1, we have an intercept. The undefined point is x equals negative 2. So at x equals negative 2, that was a vertical asymptote. Our other asymptote was at y equals 1. So when y is 1, there's our horizontal asymptote. And then we're ready to make our graph, knowing it should be positive to the left of 2. So to the left of 2, it's positive. From negative 2 to 2, it's going to be negative. So from negative 2 to 2, it's going to be negative. And then from 2 on, it's going to be positive. So we know the graph is going to be positive on the left, and it's going to bend around those asymptotes. The only way to be positive on the left and bend around the asymptote is to be in the top left corner. After we cross that asymptote, we're going to be negative, and we have to go through the y-intercept and the x-intercept. And then notice we're going to go towards that asymptote staying positive. And we now have our graph of x minus 2 over x plus 2. Let's take a look at another example where we run through these 5 things. We're going to graph f of x equals x plus 3 over x squared plus 2x plus 3 plus 2. minus 2, minus x minus 2. First, we're going to find the x-intercepts. The way we find an x-intercept is we make the numerator equal to 0. X plus 3 equals 0. Subtract 3 from both sides, and x equals negative 3. Then we find the y-intercept. And the way we find the y-intercept is we make all the x's equal to 0. So we have 0 plus 3, which is 3. Y equals 3. Over 0 minus 2, which is negative 2. The y-intercept is at negative 3/2. Undefined points. To find our undefined points. Undefined points. First, we'll need to factor that denominator. That denominator is, let's just rewrite it factored here, x plus 3 over x squared is x times x, 2 is 2 times 1, and that's negative 2 and a positive 1. There's no reducing of this fraction, so this fraction is going to have no holes in it, but we can make the denominator equal to 0. So that's x minus 2, x plus 1 equals 0. Add 2 to both sides, and x equals 2. Subtract 1 from both sides, and x equals negative 1. And those are both vertical asymptotes. This one's going to have 2 vertical asymptotes. I'm going to call it OA for other asymptotes. To find the other asymptotes, we take the leading coefficients, x in the numerator over x squared in the denominator. And because the x squared is bigger, here the degree of the denominator is bigger than the degree of the numerator, it's going to be dividing by a bigger and bigger thing. And when we divide by bigger things, we end up at y equals 0. If you divide by a lot, you're not going to have much left. Y equals 0 then is going to be our horizontal asymptote. Finally, the last thing to find is the positive and negative regions. Positive and negative regions are going to take the numerator times the denominator. In fact, we're going to take it in factored form because we've already found that. X plus 3, x minus 2, x plus 1. So we know the x-intercepts here are negative 3, 2, and negative 1. If we multiply this out, we've got x times x, which is a positive x cubed for the leading coefficients. So we know the shape is going to come up and out. Putting our intercepts at negative 3, 2, and negative 1. It's going to come up, bend, and up. Remember, x cubed, if it's positive, starts in the bottom left. And so what we find is the graph is positive from 0 to 2. Whoops, no it's not. Let me try again. The graph is negative from negative infinity to negative 2. Then it's positive from 2 to negative 1. Then it's negative from negative 1 to 2. And then it's positive from 2 to infinity. So again, it's positive from negative 3 to negative 1. Union, it's positive again from 2 to infinity. It's negative from negative infinity to negative 3. Union, it's negative again from negative 1 to 2. Our graph is going to follow that same pattern. So again, our 5 pieces of information, let's translate them onto a graph. Starting with our x-intercept was at -3. Our y-intercept was at -3/2. So on the y, -3/2, right here. Our vertical asymptote, two of them at 2 and -1. So at 2 we have a vertical asymptote, and -1 we have a vertical asymptote. Horizontal asymptote is at 0. And then we've got our positive-negative regions. So we said the graph is going to be negative from -infinity to -3. Then it's going to be positive from -3 to -1. Then it was going to be negative from -1 to 2. And then positive from 2 to infinity. So our graph is going to follow that same pattern. Let's start on the right side, because this is probably easiest to start from the right side. This one's going to be probably easier to start on the right side and work our way over to see what's happening. On the right side, you see we have to be positive and approaching the asymptote. So it's pretty clear that we're going to have to be in that top right area. In the middle, we can see we're negative, and we have to go through that y-intercept. We're also going to have to go towards the asymptotes. Notice we always stay negative, which means at some point we're going to have to bend back down and come back down negative. We can't keep going up. We can't become positive. Now the left side of this graph is particularly interesting because there's a horizontal asymptote, but we also have to go through it. So notice the graph has to start positive on the right side and go through that point. But now it's going to have to bend back and go towards that asymptote. So this graph is going to have some type of bend back to it to get it back to the asymptote, but always staying negative. So this now is the graph of x plus 3 over x squared minus x minus 2. Let's try another graph. Let's do the graph of f of x equals x squared minus x minus 6 over 2x squared minus x minus 3. Again, finding our 5 things. The x-intercepts we find by making the numerator equal to 0. And if we factor that numerator, it's x minus 3, x plus 2 equals 0. So there's 2 x-intercepts here at 3 and -2. The y-intercepts, we know we find the y-intercepts by putting 0 in for all the x's, which gives us -6 over 3, and that's going to reduce to -2. So the y-intercept is -2. Undefined points. Undefined points, we're first going to have to factor it to see if it reduces. That way we know what type of undefined points we're working with. So the numerator, we've already factored. It's x minus 3 and x plus 2. The denominator is going to factor to 2x and x. And we're getting to 3 and a 1. If we do 3 and 1, -3 plus 1 would give us that -1 in the middle. It doesn't look like anything's going to reduce out here either. So, let's make them both vertical asymptotes. We make the denominator equal to 0. 2x minus 3 times x plus 1 equal to 0. Which means x equals 3/2 and -1. When we add the 3 and divide by 2. The other asymptotes, we take those leading coefficients and reduce them, x squared over 2x squared. And the x squareds are going to reduce out here, leaving behind 1/2. So that's going to be our horizontal asymptote, 1/2. To figure out the positive and negative regions, we take the numerator times the denominator. Factored form is probably best. We'll do x minus 3, x plus 2, 2x minus 3, and x plus 1. And if we multiply x times 2x times x, we get 2x to the 4th, which means it's going to come in from a positive, wiggle, and go out from a positive. And those x-intercepts are 3, -2, 3/2, and -1. Just a quick sketch so we know what we're dealing with. 3, -2, 3/2, and -1. It's going to come in, bend, bend, and out. 4th power, going up to the positives. So we see it's positive up till the point -2, then it's negative till -1, then it's positive till 3/2, then it's negative till 3, and then it's positive to infinity. So its positive range is -infinity to -2, union -1 to 3/2, union 3 to infinity. It's negative in between there, from -2 to -1, union from 3/2 to 3. We have our 5 pieces of information. We now should be able to make this graph. First, the x-intercepts were at -3, or I'm sorry, 3 and -2. So 3 and -2. The y-intercept, that one was at -2 on the y-axis. The undefined points, they're both vertical asymptotes at 3/2 and -1. So vertical asymptote at 3/2 and a vertical asymptote at -1. And then a horizontal asymptote at 1/2. So short horizontal asymptote there. And then the signs of our graph, we're going to be positive from -infinity to -2. And it makes sense when we go through the x-axis, we'll be negative from -2 to -1. Then from -1 to 3/2, we're supposed to be positive. Then from 3/2 to 3, we're going to be negative, and then positive again from there to infinity. Which makes me look at an interesting point here. Our y-intercept is -2. But yet we're supposed to be positive in this range. That's not going to work. So let's go back and check our work and see what happened there. Oh man, let's look at that y-intercept. Ah! Here's what happened with our y-intercept. There was a -3 in that denominator that didn't get copied down into our work. A negative divided by a negative is a +2. So yes, indeed, that y-intercept should be at a +2. So let's get him out of there and move him to a +2 like we expect. Now he's going to be positive in the middle, which we expect to happen. That matches. The y-intercept agrees with the positive-negative regions. The nice part about doing all 5 parts is all your parts should agree with each other. Your positives and negatives should change at intercepts and asymptotes. Your y-intercept should agree with the positive-negative regions. Sometimes students skip the positive-negative regions and they miss errors they would have otherwise caught. So please take the time to find all 5 parts because it's really going to help you see what happened. So now as we fill in, close to the asymptote, we start positive, go through the point to turn negative. It's the only way that would have made that graph work. Now starting with the asymptote, we come down, we're positive like we expect, go through the y-intercept, and then staying positive, so we have to go back up. And then finally the right side, close to the intercept, starting negative, and then turning positive, going towards that that horizontal asymptote. This is the graph of x squared minus x minus 6 over 2x squared minus x minus 3. All 5 parts. Filling in the blanks. Let's do another one. It's a little tricky trying to remember what parts we do. The whole key to learning this process is to practice, practice, practice. So you know what piece to go for, where to find it, and how to use it to make your graph. Practice, practice, practice. If f of x equals x squared minus x minus 2 over x plus 2, we're going to graph this. Starting with the x-intercepts. The x-intercepts come from when the numerator equals 0, so when we factor that numerator, it's x minus 2 times x plus 1. Make it equal to 0, and then it's clear that our x-intercepts are at 2 and negative 1. Y-intercepts, we get those by making all the x's equal to 0. This time we're going to be careful of our signs, giving us negative 2 over 2, which reduces to y equals negative 1 for the y-intercepts. The undefined points, we need to first factor that numerator in so that we can see if it reduces, so we know what type of undefined points we're working with. We said it was x minus 2, x plus 1 over x plus 2. Nothing's going to reduce, so that denominator equal to 0 is going to be a vertical asymptote. So x equals negative 2 is a vertical asymptote. Other asymptotes? You'll notice on the other asymptotes, the exponent in the numerator, the x squared, is bigger than the x in the denominator. This means we're going to have some type of slanted or curved asymptote. And the only way to get it is to do the long division implied by the fraction. Now, fortunately, this fraction, the denominator is x plus 2, we can use synthetic division with negative 2 coming out. So negative 2, 1, negative 1, and negative 2. We're going to synthetically divide the denominator into the numerator. Gives us 1, negative 2, negative 3, 6, and 4. So it's going to be 1x minus 3 with a remainder of 4. With slant asymptotes, we don't care about the remainder. The remainder tells us we're getting closer to x minus 3, but we're not actually going to hit it. The actual function itself tells us the slant asymptote that this graph is approaching. Y equals 1x minus 3 is our slant asymptote. That means on the edges the graph is going to approach a diagonal line. Last thing to find then is the positive and negative regions. To do that, we make the numerator times the denominator using the factored form, x minus 2, x plus 1, x plus 2. So the x-intercepts are 2, negative 1, and negative 2. Notice it's a cubic, 1, 2, 3 x's, and it's positive, so it's going to come in, wiggle, and go out. 2, negative 2, and negative 1. So it's going to come in from the bottom because it was positive, wiggle, and go out. And all we care about here is the sign. Negative on the left side, positive for a while, then it's negative for a while, and then it's positive to the end. So it's positive from negative 2, whoops, that's supposed to be negative 2, and positive 2. That's what I get for moving too fast. Let's get rid of a tick mark. Not the whole axis. Get rid of a tick mark. There we go. Now it's at 2. From negative 2 to negative 1, it's positive, and then union, it goes positive again from 2 to infinity. Negative is everywhere else, from negative infinity to negative 2. Union, it's negative again from negative 1 to 2. Now we're ready to graph our function. Starting with the x-intercept, which we said we're at 2 and negative 1. 2 and negative 1. The y-intercept's at negative 1. So negative 1 for the y-intercept. Undefined, we have a vertical asymptote at x equals negative 2. We have a slant asymptote at y equals x minus 3. We should know that has a y-intercept of negative 3 and a slope of rise 1, run 1. So if we make a couple dots to give us an idea of where this graph is going. There's our slant asymptote. So we might need to extend a few lines just in case here. Okay. Then our positive negative regions, it's negative from negative infinity to negative 2. Then it's positive from negative 2 to 1, negative 1. Then it's negative from there till 2, and then it's positive from there till forever. Let's do the middle first here. We can see the middle of the graph, we're close to the horizontal asymptote. We go through our points, and then it has to start going close to that asymptote. Notice that perfectly follows the asymptotes. It perfectly follows the positive negatives. It also goes through all the points. That matches everything. On the left side of the asymptote, though, we have to be negative the whole time. So if we're going to start close to the asymptote and be negative, we're actually going to be down here, and then we have to bend and go towards the slant asymptote. So this one has its slanted part down below. So all that together becomes the graph of x squared minus x minus 2 over x plus 2. I have one last example I want to do then. F of x equals x squared minus x minus 6 over x minus 3. And in fact, you know we're going to have to factor everything. And so what a lot of people start doing is they start factoring at the beginning rather than halfway through and doing it halfway. So let's factor it. It's going to factor to x times x, and to get negative 6, it's going to be negative 3 and positive 2. So we've got an x minus 3 in the denominator. And one thing you probably notice is those x minus 3's are going to divide out. That's going to be significant to us here in a minute. So when we're finding our x-intercepts, those points that have divided out really aren't going to be a part of it. So while we make the numerator equal to 0, we only have to take what's left to equal 0, which is nice. X plus 2 equals 0. And so when we subtract 2, we get x equals negative 2 for our x-intercepts. Our y-intercept, again, we only need to take what's left and plug 0 in there. So we have 0 plus 2, or y equals 2, for our y-intercept. Our undefined points are when the denominator equals 0. But notice, after we reduce, there's nothing left in the denominator. This means we don't have any vertical asymptotes. However, we still have an undefined point. This is the piece we don't use very often, going all the way back to the beginning, but when we do, it becomes important. If we can divide out something, we get a hole in the graph. So down where we are, that x minus 3 that divided out, if I can get the right color, that x minus 3 that divided out, solving that gives us x equals 3. That isn't a vertical asymptote, that is a hole in the graph. We'll talk about what that looks like in a minute. Other asymptotes? Well, after we reduced, all that was left was the x plus 2. There's really no division to do. Really, it's just approaching the line y equals x plus 2. In fact, we're going to find something very interesting about that line y equals x plus 2 here in a minute. In terms of our positive and negative regions, graphing what's left after we reduce x plus 2 gives us just 1, 0 at negative 2. In fact, we know that x plus 2 graphs as a straight line. And so it's going to be negative on the left and positive on the right. It's going to be positive from negative 2 to infinity. It's going to be negative from negative infinity to negative 2. So let's put this information on the graph. The y-intercept, the x-intercept is at negative 2. Let's start there. The y-intercept, I think, was at positive 2. Yep. There's a hole in the graph at x equals 3. The way we're going to find where that hole is we're going to plug that 3 into the remaining stuff. 3 plus 2. 3 plus 2 is 5. So 3 comma 5, there's going to be a hole in the graph. So at 3 comma 5, there's a hole in the graph, and it should be orange. I'm using the wrong color. In terms of asymptotes, it's going to be getting really close to x plus 2, but what you actually see is this graph is following actually the line x plus 2. The asymptote is the graph. In fact, this is just a straight line with a hole at 3, 5. But that kind of makes sense because this whole time we were making our graph, we said we were going to focus on the part that was left after we reduced. What was left after we reduced was x plus 2, and so what's left in our graph is the line x plus 2. We just have to account for the hole that we divided out. So that's how we graph these rational functions. We find these 5 important pieces of information. First, we find the x-intercepts by making y equal to 0, or essentially the numerator equal to 0. Then we find the y-intercepts by making all the x's equal to 0. Then we find our undefined points. Generally, that's going to be a vertical asymptote, but sometimes it's a hole in the graph. Find our other asymptotes. It's going to be a horizontal asymptote if the denominator is greater than or equal to the numerator in terms of degree. We either reduce or end up with a 0. But in the rare event that the denominator has a smaller degree than the numerator, we have to use long division in order to find that curve that it's going to get close to. And finally, we found the positive and negative regions, and that helped us identify the signs of our rational function. These are going to take practice to get all 5 of these processes down, knowing what to find, where to find it, and how to use it. Once you get a good practice with that, you'll be ready to go. So we will see you in class tomorrow.